So hi everyone. Today we have the pleasure to have Agnieszka Janiuk presenting her work on GRB-like objects, let's say, and numerical simulations. So feel free to start when you want.
Okay, thank you very much, Rafael, for inviting me to give this seminar. And I'm happy that the audience is interested in our research that we are doing in the Center for Theoretical Physics of the Academy of Science in Warsaw, where I work, and I'm leading the Relativistic Astrophysics group here. And my seminar will be about accretion-ejection coupling in multi-messenger transients, and in particular, we are studying collapsars and short gamma-ray burst engines, and these quints are process nucleosynthesis. So let me start with the introduction. Transients, what are the transients and what is multi-messenger astrophysics? So the transient phenomena typically involve compact objects, black holes, and neutron stars. These are the most interesting ones for me. And these transients are very short in time, because we have only a few seconds or minutes to observe the main characteristic of the events, such as these very bright explosions observable as gamma-ray bursts. But as for the multi-messenger aspect, we also expect to have other complementary non-electromagnetic signals. In particular, the gravitational waves are interesting counterparts of these transients. And in this talk, I will discuss our works first on the collapsar jets and collapsar disks that also recently are found out to be additional possible sources of gravitational wave transients. Then I will discuss the accretion disk quints as the source of lower energy transients, namely the kilonovae associated with short gamma-ray bursts. And in the end, I will mention briefly some ideas about the chemical enrichment from the kilonovae and collapsars in our galaxy and in our universe. So for those of you who are not very much familiar, I hope everyone knows gamma-ray bursts, but just to define the objects, they are rapid, bright flashes of radiation peaking at gamma rays. So it is up to MeV range in energies, and they are observed by satellite missions placed in the orbit around the Earth. They found out to be uniformly distributed on the sky, so that means that they do not come from our galaxy, but from very large distances and cosmological distances, and observed total isotropic energies are very huge, 10 to 55x, but considering that they are beamed sources of radiation, so the radiation is pointed towards our line of sight, that reduces actually the energy produced at the source to about 2 orders of magnitude less. But still, they are very, very bright. And as you see here, a lot of missions were devoted to understand these sources. So what we know so far from the works in 1990s already, this gamma-ray burst emission must come from the jets, because it has to be beamed in the very narrow angle. And also this conclusion was supported by the fact that the gamma-ray spectra are observed to have non-thermal energy distributions. So to avoid the compactness problem, the huge optical depth would produce pair, electron-positron pair, and would give rise to thermal emission. So in order to avoid that problem, the relativistic fireball expansion model was proposed with this very high speed. The bulk Lorentz factors in the gamma-ray burst jets exceed gamma of few hundred, 100 at least, in contrast to the jets produced by persistent sources such as blazars, for instance. Okay, so we know that there are two classes of gamma-ray bursts. These gamma-ray bursts are classified in a standard way to categories of short and long GRBs. They differ from each other with respect to their hardness ratios and duration times. This T90 is between a fraction of a second and up to several hundred seconds. And you see here clearly the two distinct groups statistically categorized, and it has been known for a long time already that the long gamma ray bursts are identified with the supernovae type 1 BC, while the short GRBs only quite recently in 2017 have been proved to originate from a compact binary merger. In particular, this compact binary merger was a double neutron star that arose also in counterpart with the gravitational wave emission and the prompt gamma ray burst signal observed by the Fermi and integral satellites. So there are two classes of GRBs and two classes of progenitors that are discussed in this context. So for the long GRBs, we have this massive star that is collapsing, forming due to the core collapse process, it is forming a neutron star and a black hole in the end after this transient neutron star could collapse to a black hole. And along the rotation axis of this newly formed black hole, there must be a jet launched from the central engine. The central engine is composed of a remnant accretion disk that is formed from some part of the matter of this collapsing star from the fallback process. On the other hand, the compact binary merger also results in kind of this similar structure, while the mass of the disk is much smaller and there is much lower amount of mass available for accretion. That means that also duration of this process is much shorter, and we have a plausible central engine for a short gamma ray burst from the compact binary merger progenitor. And both of these types of progenitors are resulting in formation of a relativistic jet that is the source of power for the gamma ray emission. But as for the relativistic jets, they are common in the universe. I already mentioned you the jets in blazars. But anyway, they are observed at different mass scales from accreting black holes. And all these jets need a central engine with magnetic fields. They are anchored in the accretion disk and penetrate the black hole's ergosphere, which helps to mediate the process of energy extraction from the rotating black hole. This process is known already from 1970s as postulated by Blandford-Znajek, and the Blandford-Znajek powered jets are a plausible mechanism for the source of power of gamma ray burst jets. We went from 1980s and cartoon type of figures that were drawn to visualize the evolution of the accretion disk magnetosphere and formation of the open magnetic field lines along the rotation axis of the black hole. Up to very recently, there are these state-of-the-art numerical simulations that in 3 dimensions also are able to reproduce this kind of structures like the winded up magnetic field lines that are helping to accelerate the jet along the rotation axis of the black hole. So what is now the current state-of-the-art methodology used in this kind of research is the general relativistic MHD simulations. So the MHD simulations are based on MHD equations. So these equations are written here. They are known from physics as continuity and energy momentum conservation equations here proposed by Euler in the past. Maxwell equations also describe the evolution of the magnetic fields. Here the stress energy tensor is composed from the matter and electromagnetic parts, so this accounts for the evolution of mass and evolution of the gas energy and evolution of the magnetic field. And all of this has to be embedded in the 4-dimensional space-time to account for the very strong gravitational potential of the black hole that sits in the center of all of this. And numerically, we need to solve these equations. So we have to discretize them on the grid. Typical methods used in the numerical codes are the finite volume methods, while we advance through our numerical scheme the vector of variables via the fluxes over the cell boundaries, and considering also some source terms at the cell centers. These numerical schemes are used to advance the conserved variables in times, but also what is important here in GRMHD, there must be an important part of this code provided to solve the inversion scheme that is used to recover the primitive variables from the conserved ones. The conserved ones are the stress energy tensor components, very complicated formalism, but the primitive ones are needed to describe the equation of state. And I will mention later why this equation of state is important, specifically in the context of gamma ray burst accretion disks and their model. All right, we developed here in our group the version of the code named HARM. This is the acronym standing for the conserved scheme for high accuracy relativistic magnetohydrodynamics. It is quite old code, but our implementation actually accounts for additional features that describe the neutrino cooling and the Fermi gas equation of state. So we account for tabulated relations of the pressure and internal energy of the gas from density and temperature in the gas, because these densities and temperatures are very huge in the physical sources that we want to model. And we have additional modules also added quite recently to the code to account for the evolution of the Kerr metric due to the black hole growth and its spin changes, which is important in the transient phenomenon. And most recently, with the self-gravity added to the collapsar simulations through the perturbative terms. We also have 3-parameter equation of state, so not only the pressure and internal energy depends on density and temperature, but also on the chemical composition. I will describe this more in the second part of my talk. And we have this neutrino leakage scheme to follow the neutrinos emitted from the accretion disk. So we can produce these jets with kind of simulation that is solving GRMHD equations on the grid. Here you see example snapshot of one of our 2-dimensional simulations actually. So on the leftmost panel, you see the density distribution. You see the presence of the accretion torus around the black hole that is residing here in the point 0 in the center of the grid. And you see this disk is very dense, while the clean, very low density funnel has been formed along the rotation axis of the black hole. And this very low density funnel is actually very highly magnetized. This second panel shows that this is the magnetization in logarithmic scale. So magnetization is defined here. So it is the ratio of the electromagnetic energy to the total energy of the gas, and the characteristic also energetics parameter, that is the ratio of the TRT stress tensor component to the rest mass flow density, is visualized here in the second panel. This quantity is quite important because it will give us a proxy to the ultimate Lorentz factor that is achievable by the jet at infinity. This quantity, total energetics parameter, consists of the enthalpy part and the Poynting flux part, and it is a sum of the thermal and Poynting energy in the jets. So that's why we understand that while this whole energy is converted to the bulk kinetic energy in the jet, it may give us a bulk Lorentz factor at larger distances. While our simulations are focused on the central engine, so you see here the distance scale is up to few hundred or in some cases we study larger, but still on the order of 1,000 gravitational radii from the central black hole. So it is a base of the jet here. All right, so let me go from this introduction to our recent results and recent works that we are doing in my group. So first topic is devoted to the collapsars, study of collapsars. Again, the collapsars originate from collapse of massive rotating stars. The star must possess enough angular momentum before it collapses and forms a black hole to allow for the formation of this rotationally supported accretion disk around the black hole. And this accretion disk will mediate the energy extractions from the black hole and mediate the emission of the jet. Our recent works are adding kind of interesting feature to this collapsar phenomenology and numerical studies, because we can account, in contrast to the other groups, for the growing black hole during the collapse process. So co-rotation allows for the formation of the mini disk at the equatorial plane. You see here how this mini disk has formed in the center of collapsing star, but also the mass and angular momentum of the black hole will change in time because of the mass flux and angular momentum flux through the horizon. It is integrated over the horizon sphere at each and every moment during the time-dependent simulation. And in consequence, our space-time Kerr metric, so this G mu nu coefficients will change in time due to the increase of the mass of the black hole and changes of the spin. Changes of the spin does not mean the spin may only increase. It may also decrease. And I will show you that actually spin down of the black hole is obtained in many of our models. In the initial condition, we normalize our angular momentum of the star to the critical rotation that allows for the gas to circularize around the innermost stable circular orbit. And here you see some results obtained in 2021 by my master student, Dominika Król, who studied two-dimensional models of evolving black hole in the collapsar. With either hydrodynamical, so GR hydro neglecting the magnetic fields, or also MHD models with initially assumed poloidal field configuration. These are the results for unmagnetized models to start with, because it was easier to compute, and the net black hole spin-up was possible only for very small range of parameters adopted here. This S parameter means actually how much the angular momentum of the collapsing star at the ISCO exceeds this critical angular momentum. So 1 and above 1, net spin up of the black hole is possible. This is the final spin of the black hole mapped here with the color scale, depending on the assumed initial spin and this rotation parameter. So as you see here, for most of the parameters studied in this master thesis, she obtained quite low final black hole spins between 0.2 and 0.4 in dimensionless units. Yeah, this Kerr black hole was spinning down in the end of the simulation, and it was actually studied independently by later authors who also confirmed finding such equilibrium spin values of this same order. So you can look at the work of Jacquemin Ide, who published these results also in 2024. What we did next here in this code was adding the self-gravity in the collapsar. So not only the mass and angular momentum of the black hole will evolve through the fluxes of the mass and angular momentum over the black hole horizon, but in addition, we also consider now the perturbative terms due to self-gravity of the core above the horizon. So it was postulated already by Teokolski, and we use this similar formalism from the Teokolski equation. And this is expressed here. These two additional terms through the perturbation from the horizon to a given point in our grid, the matter and angular momentum terms are integrated, and they also add perturbations to the Kerr metric, and this is our formal method to compute monopole self-gravity. So to stress, again, we have only radial direction considered here, but this accounts for the self-gravity of all this mass that is enclosed above the black hole horizon within the orbit of a given particle in the collapsing star. These results have been published in 2023, again with Dominika and also with another co-author of our work, Narges Shahamat. And here you see resulting profiles of the black hole evolution, the mass of black hole on the left and the spin of the black hole on the right. And you can see clearly the difference between the evolution of the black hole spin and mass when the self-gravity is accounted for. These are these thicker lines. Self-gravity can actually significantly speed up the evolution of the collapsing stellar core, and the spin up and spin down is achieved much quicker than in case of the non-self-gravitating collapsars. Again, all of this depends on the assumed initial normalization of the angular momentum in the collapsing star. So we found this temporary peak in the black hole spin is corresponding to dramatic increase of the mass accretion rate. We found also fluctuations in this mass accretion rate, and we found that they are related to arising inhomogeneities in the density and pressure of the gas in the collapsar. This pressure is here in this small map. Some of these models were embedded with a dipole or vertical or uniform magnetic field, and interesting effect of the repulsive magnetosphere was found. Magnetically arrested state of accretion also developed in the core for some of the models that we studied. Here you see this result of the phi madness parameter that is defined as the ratio between the magnetic flux on the black hole horizon over the mass accretion rate times Rg times C. So it is dimensionless quantity. If it is above some threshold, people define this as a kind of magnetically arrested state. And we found this magnetically arrested state to be actually present in many of the models, but not in all of them. For dipole models, we didn't find mad state forming in the collapsar in this simulation. But it was interesting later to find out actually if we can produce jets. We thought that to produce jets, we need a mad state, and we went also from the 2D unmagnetized and magnetized simulations to the full 3D case very recently. These are the results from the master thesis of another student of mine who just finished this work and published in Astronomy and Astrophysics 2026. You can find this article on arXiv. So here we present the 3D simulations for models with mad state that has been developed. We observe jets and estimated their energy to be few times 10 to 53 ergs per second. So it is a quite good energy range for the power of the long GRB. The bright GRB can be produced from such a collapsars. But again, this self-gravity has been found to be an important feature of the model, which is so far neglected by most of the other group simulations. And what we found is this temporary jet quenching, even in the very strong magnetic field when the mad state is formed and at the interval of a rapid accumulation of the mass and enhanced accretion rate, we found the temporary jet quenching. So you see here in this middle panel, because in the left panel and right panel, you see stages where the bright jet is produced, but here the jet gets very narrow, and actually we measure the drop of the bulk Lorentz factor and reduction of the opening angle of the jet due to the extra pressure and exerted on the jet funnel. You see these results here as a function of time for the simulation that I presented in the previous snapshots. So we define this as a quiescent interval in the jet emission. The quiescent means that this phi mad magnetically arrestedness parameter drops below the value of interest, around 20 or 40, drops to an order of unity only in case of the self-gravitating model. For comparison, we see here with this yellow line the non-self-gravitating case with the same setup, and the self-gravitating case results in this temporary jet quenching. Then the madness parameter increases again, and also jet efficiency, which is expressed here in percent. So this is the jet power over the accretion power, m.c square. It is about 10% at the beginning, but then for non-self-gravitating case, it is quite large for most of the duration of our simulation, but at the self-gravitating case, it drops very much. And the same for the jet opening angle on the right. So the jet opening angles are estimated either from this sigma distribution or from the Lorentz factor at infinity distribution. They are about 10, 15 degrees. And in this quiescent interval, the jet opening angle gets very, very narrow. What is interested in the simulation appears also very recently. And we studied this in the next follow-up work. So these are the collapsar disks as a potential gravitational wave sources. We are in the preparation of this work, so I will not discuss much of this result, but I would like to highlight, because this is a very interesting topic as well. It has been proposed a few years ago that Rossby wave instabilities may operate in the cooled accretion disks in the collapsars, and they may induce gravitational wave emission due to non-axis symmetric spiral arms that are forming here. What we found after we added this self-gravity effect is that these low-order azimuthal modes are amplified. This is the self-gravitating case in comparison with the non-self-gravitating. And we want to discuss this as a potential additional source of gravitational waves that may be detected in the 100 hertz range with amplitudes that are potentially even larger than those proposed for core collapse supernova. All right. What I discussed so far were the collapsar jets that are produced inside small volume, so inside the vicinity of the central engine that is launching them. However, we want to propagate these jets throughout the star. The star is quite huge, so we want to go from the regions around 10 to 3 gravitational radii, which is 10 to 8 centimeters for 10 solar mass black hole, up to the distances of this star size, or the stellar core size, 10 to 11, 10 to 12 centimeters. So for that, we needed to adopt another tool. So we took a different code and different initial condition as well. So we wanted to study more physical initial conditions with evolved star models, compare some distinct types of progenitors of the pre-supernova star. These models were taken from Woolsey and Kerr and also computed as a carbon-oxygen core evolved with the MESA stellar evolutionary code. And we put that into the initial conditions for the code that is called the black hole accretion code. That code is better to study large-scale propagation of jets because it is featured with adaptive mesh refinement, which allows to cover much larger spatial and temporal scales. On the other hand, it neglects still the black hole evolution and self-gravity, so I cannot discuss here these features. Anyway, what we wanted to study, and I mean here mainly my postdoc, Gerardo Urrutia, who is the author of this work that I'm reporting here now, he was interested in jet launching and breakout from this collapsing star and see if the successful breakout of the jet is possible and when and for which initial conditions. So for the initial conditions, he also imposed a magnetic field of a dipole-like configuration or hybrid configuration. If interested, I can give you the reference to see how this hybrid is defined. Anyway, for both of them, for both of these magnetic fields and all these types of progenitors, he was actually sort of able to produce jets, but with the different energies. So energies below 10 to 51 up to 10 to 53, depending on the progenitor type and on the strength of the magnetic field and on the configuration of the field assumed at the beginning. What is found also is that the jet luminosity peaks, these peaks reflect efficient conversion of thermal and magnetic energy to the bulk kinetic. So again, this formula that I provided before, thermal plus Poynting energy, together give the Lorentz factors achieved in pulses reaching above 100 and give the jet efficiencies here, not in percentage, but in numbers, reaching 100%. And finally, the breakout times between 1.8 seconds to 3.5 seconds until this jet reaches the end of our star. So the breakout through the envelope is found to be like very, very fast for some type of the progenitor. This M16Ti, whatever that means, from Woolsey and Heger's work, was found to be the most plausible progenitor for a fast jet. And gravitational waves, because this is a hot topic again, not only for the accretion disks in the collapsars, but also for the jets in the collapsars. They have been invoked to be also sources of gravitational waves, where the acceleration of the blobs in the jet may be responsible for this gravitational wave propagation and memory of gravitational waves carrying together with the jet. This is the follow-up work that we are now ongoing. So basically, Gerardo Urrutia and Fabio De Colle are leaders of this paper. It is in preparation, but I want to show you the preliminary results that are showing the detectability of the gravitational wave from collapsar jets. So what is found here, this detectability is quite promising for some of the proposed instruments, the SIGO or baryonic observatory, while more energetic jets would be detected at higher frequencies, for instance, by the new Einstein telescope. Okay, so that was the second part of my first part of my talk, and now going to the second part of my talk, I want to focus now on the compact binary mergers. So we leave the collapsars, we leave the long GRBs, we now go to the short GRBs, and we have several interesting results to tell you about the compact binary mergers, and in particular the influence or the contribution of compact binary mergers, accretion disk wind, post-merger accretion disk wind to the kilonova phenomenon. So what is kilonova? Let me start with this famous source, GW170817. This is the source when the gravitational wave was observed together with the gamma ray burst, actually not exactly together, but there was this time delay of 1.7 seconds. Let me show it again here. This is this 1.7 seconds between the merger and the GRB prompt. So this 1.7 seconds was attributed to the hypermassive neutron star existence and then collapsed to a black hole. But what is also important, after this gamma ray burst has been observed, there was a rapidly fading electromagnetic transient in the same galaxy, in the same host galaxy, observed over a few weeks after the event, and this electromagnetic transient appeared here and was modeled as a kilonova. Kilonova is actually a term proposed much before, a long time before, and it is suggested that the double neutron star can eject material during their in-spiral phase. This material is rich in heavy radioactive isotopes, which can power an electromagnetic signal. Dynamical ejecta from compact binary mergers must be sufficiently massive and sufficiently fast to emit about 10 to 40, 10 to 41 ergs per second in a timescale of about 1 week after this compact binary merger emitted this ejected material. Some putative kilonova has been proposed in 2013, but it was not measured with enough precision, so people had only a few data points to discuss the effect of kilonova bump that is arising here a week after this short GRB 130603. But now, with this GW 170817, the system was much better studied thanks to multi-wavelength and multi-telescope campaigns, and the transient called SS178 associated with GW 170817 was modeled in range of wavelengths from optical to infrared. And the kilonova signal produced by the radioactive decay of elements was modeled and fitted to this data. And what was actually proposed was that there are two components, blue and red kilonova components appearing at different times in this source. So the first was the blue kilonova, the second one appearing after some time was this red kilonova signal. The schematic idea sketched here attributes these two kind of signals with different color to either a pre-merger tidal tail or the post-merger emission from the accretion disk wind with different speeds and different composition. The composition is important because the kilonova colors are named here red and blue, but actually what they arise from is the opacity of the medium of the gas due to the presence of specific elements from the family of lanthanides, and these lanthanides they are absorbing photons and they are the ones who are responsible for the red kilonova color. While the lanthanide free medium should be responsible for the blue kilonova color. This is the old simulation of the light curves assuming some mass of the ejecta and some velocity of ejecta and different compositions. And again, we are studying our models taking into account the R process nucleosynthesis in the accretion disk wind ejecta. And now we consider this neutronization. Neutronization means that the number density between protons and baryons is much lower than 0.5. If it is on the order of 0.25, we obtain heavy elements from the first peak of our process nucleosynthesis. It is here. It is gallium, germanium, strontium. These are the elements of the first R process peak. R process works like that we capture more and more neutrons on the nuclei, and if we have more and more neutrons, we can produce more and more elements from the second and also third peak. So third peak here, the actinides are obtained for very low electron fractions, meaning very high neutronizations. And in between, we have those lanthanides, which I mentioned already, lanthanides responsible for the opacities in the kilonova and the red color of the kilonova. And we have a third peak of the R process, also interesting elements for us. There's gold, platinum, and elements interesting for us on Earth. Even though their abundance is not very high, they are important for our industries. So from our code, we can follow the trajectories of the particles where the mass is ejected or accreted. And now I will focus not on the jet, because the jet is baryon poor and whatever the composition, it is meaningless for the kilonova studies. But I will focus on the wind here. So in the intermediate latitudes from the accretion disk body, this is the initial condition, and the trajectories that are escaping from this accretion disk with the velocities fast enough to make them unbound from the gravitational potential of the black hole. These trajectories actually follow the magnetic field contours. So this is the magnetically driven wind from this central engine. And we trace these particles as passive Lagrangian particles that store the data about density, velocity, and electron fractions, so chemical composition in the outflow. And by means of the post-processing, we compute the R-process nucleosynthesis of this tracer data to obtain the chemical evolution of the wind and to obtain further elements starting from hydrogen and helium. We obtain further and further elements on this evolutionary track, so to say. So this is the plane neutrons versus protons content in the nuclei. And the nuclei, unstable ones, are forming here in this unstable path, reaching eventually the stability path in the nucleosynthesis pattern. So we obtain heavy elements up to mass number of 200, including the platinum and gold in the disk ejecta. Using the code named Skynet, provides nuclear reaction network and is capable to trace the nucleosynthesis on the R process with a large database of over 1,000 isotopes of these elements. So all these unstable isotopes that are decaying radioactively are considered here in this database. This is the result from one of the older simulation, abundance pattern extrapolated over the time versus mass number of the element. Individual trajectories of the wind from accretion disk are marked here with the gray lines, and the average profile is this red one. And in comparison to the solar abundance pattern, we are interestingly obtaining the second and third peak of the heavy elements that are matching the observational data quite nicely. What is done more recently with our code, because this result which I showed just on the previous slide was obtained from the two-parameter equation of state simulation. Now we have more precise three-parameter tabulated equation of state, Helmholtz equation of state with a neutrino leakage scheme, and three-dimensional simulations of the disk accretion in short GRB engine. So this simulation snapshot is visualized here. We have this dense accretion disk in the center of the central engine, and we have accretion disk wind. The velocity field is visualized here as a vector field, and these velocities are actually subrelativistic. These are like 0.1, 0.2 speed of light, but still fast enough to escape our boundary, our simulation boundary, and escape as a wind to infinity. Chemical evolution of these winds produces lanthanide-rich media depending on the engine properties, which we consider to vary across the ratio of the black hole mass to the mass of the disk, across the magnetizations and black hole spin values. I'm not listing here all of these cases that we studied, but we studied quite a lot. And we found in some models the lanthanide mass fraction is actually quite substantial, 0.03 in this group of elements, isotopes. Also, the characteristic quantity that is interesting for people studying chemical compositions are the number ratios between europium and iron, also quite large in some of the models. And favored models for the rich red kilonova contribution from the accretion disk wind is this one. So we have quite a favorite model to be attributed for the red kilonova contribution from the accretion disk wind. It is quite interesting feature. What we also discuss here is the chemical enrichment by the GRB central engine in general. So this is the range of ejecta masses that we produce. These ejecta masses are up to 0.1 solar mass here for those models. And chemical enrichment in terms of the ratio between heavy and light elements. The threshold is at 130 mass number. Mass number 130 corresponds to the second peak of the R process nucleosynthesis. And we see that these quite massive and rich in heavy elements these winds can be produced from our simulations, whatever 3D or 2D cases as well, but of course 3D are more precise in our opinion, and they are more adequately describing the acceleration of the wind through the magnetic fields. Broad range of electron fractions and velocities up to 0.2 speed of light are obtained, leading to various nucleosynthetic patterns and heavy to light elements dependence on the central engine properties. And what about the jet? I need to mention, because this was the question from our referee. The paper was not focused on the jets, was focused on the chemical evolution of the disk wind, but still for GRB it is actually quite important to argue that this source also has a jet. So we can compute, of course, the Blandford-Znajek luminosity for these kilonova models, and compare it with the neutrino luminosities that are possible to obtain from the neutrino leakage scheme that is used here. And what we see is our disk did not reach the magnetically arrested state here in this pair of simulations, and the jet luminosities are quite low. So this Blandford-Znajek process would give us about 10 to 51 ergs per second, while the neutrinos about the same, because the neutrino luminosity, neutrino and antineutrino will annihilate, and then we can have some, of course, efficiency considered, but 10 to 51 is also the range of energies that we can obtain from neutrino annihilation. So our conclusion is that the jet in the kilonova related GRBs may be driven by neutrino annihilation rather than the Blandford-Znajek process, or both at some favorable case, and the standard and normal accretion evolution of the disk will lead to more powerful winds outflows and a weak jet. Additional effect of the disk wind is the collimation of jet, whether it is weak or strong, but it will be a narrow thanks to the pressure exerted on this jet funnel from the accretion disk wind, and this was studied in a complementary work again by the postdoc Gerardo Urrutia in 2025. He studied disk winds from GRMHD simulations remapped to the large-scale jet propagation model, and then the larger scales he found the jet and cocoon together are collimated due to the disk wind, in addition to the post-merger dynamical ejecta. I need to differentiate between this post-merger dynamical ejecta that can have some kind of spherical shape and impose some effect on the jet and cocoon propagation. But we have a different medium here. We have this accretion disk wind that is actually much more important, in our opinion, to affect the jet opening angle and the jet profile, the jet energetics, the evolution of the kinetic and thermal energy, and so on. So all these details are in the paper led by Gerardo Urrutia last year. So I think I need to conclude my talk. There is several puzzles that we wanted to address in these works. So for instance, the puzzle of the kilonova from a long GRB. There is a source known for several years already, GRB 211A, which is the minute-long gamma ray burst. So something that would suggest us to have a collapsar as a central engine, but there was no association with a supernova in the source. There was only a kilonova detected. The kilonova was actually very similar in its characteristics to the source from the 2017. However, there were no data in gravitational waves available at that time of the source, so people could not conclude whether it was a compact binary merger, and if so, whether it was a binary neutron star or neutron star and a black hole. And still the puzzle remains. Can be exceptional binary merger with a very long tail, very long GRB emission, or the exceptional collapsar, which would not produce a supernova but would produce a kilonova instead, or some other type of progenitor as well, such as the ones involving a white dwarf. So discussion is now ongoing in the literature. People proposed neutron-star black hole merger to explain the massive ejecta with low velocities, but again, it's not clear if this formation channel is strong enough to produce such a source. Then the R process enriched collapsar was proposed by other researchers, but here the people must have fine-tuned the parameters of these collapsars very tiny, and also they obtained quite large velocities of these kilonova ejecta, so it is not conclusive work. Our speculation here is that we can have eccentric merger, either double neutron star or maybe a black hole and neutron star. We do not model the merger itself, we model only the post-merger system, so we can assume just a mass ratio between the disk and the black hole, post-merger black hole format. But the massive disk and prolonged accretion prior to the magnetically arrested state, when we still have not reached this mad state, is possible to emit weak jet in our scenario. And what about these heavy isotopes? Can they be formed in any of the GRB environment actually? So do the collapsars and supernova explosions and compact binary merger contribute to the formation of heavy elements in our periodic system of elements, and which are more important? This is a controversial diagram. I heard from people already, but it is very old, and actually we can color it with the different colors to state that these merging neutron stars are forming the actinides, while the dying low mass stars and exploding massive stars are forming other groups of elements, but still it is not that clear which ones are important, and actually all of them should contribute to the chemical composition of the universe, because the solar system abundance pattern results of multiple generations of stellar nucleosynthesis that account for first explosion of the supernova, formation of the compact remnant, and then merger of the compact remnant with the companion, and subsequent enrichment of the environment with the heavy elements from the next generation of the stellar evolution. So multiple supernova explosions are required to form elements like iron and nickel within 100 parsecs from the sun. These lanthanides and actinides from the families, these two families, the elements can be produced in both mergers of compact objects and also in the core collapse supernova. Then if mergers, then whether it is a black hole or neutron star and neutron star merger, or a double black and double neutron star, it is disputable recently. Because on one hand, the black hole neutron star mergers may give more massive ejecta, which are better for formation of the heaviest elements. But some numerical simulations give massive ejecta also from double neutron star mergers with some favored conditions. It is all embedded in the details of these numerical simulations, and different groups obtain different results. And for the delay times, so delay times means how fast this coalescence will appear over cosmic time. It may be between mega and gigayears. So black hole neutron star mergers in general are postulated to have shorter delay times, so they will more frequently embed their environment with the heavy elements. However, distinct population of the neutron star mergers within 100 megayears delay times are also discussed. So it is very fresh, very hot topic now, and research is needed to make conclusive statements. Let me come to my summary. So what I presented in this talk was mainly the research on GRBs, gamma ray bursts, that are spectacular phenomena that lead to variety of observables in multi-messenger domain, current and potentially future observations. We use computational astrophysics methods of general relativistic MHD to model the GRB jets from strongly magnetized plasmas in extreme gravity. We find that collapsar jets break up through the star's envelope for strongly magnetized progenitors. The self-gravity of the star is an important effect and may alter the jet properties, its opening angle and energetics, and may also lead to temporary jet quenching. The uncollimated winds from central engines are sites of heavy elements nucleosynthesis. They may contribute to jet collimation and kilonovae emissions. And we now face many open issues for discussion. Disks and jets are sources of gravitational wave emissions. The chemical enrichment of the galaxy from various progenitor populations is appealing. So thank you very much for your attention. I want to acknowledge my group, first of all, the people who were involved in this research, so PhD students and postdoc, and also computational resources through which we are able to obtain kind of simulations that we present here.